Okay? All right, so let's move on. So last time we covered perturbation theory, time-independent and time-dependent approach. And so the ideas there are quite similar. We introduce the method to solve unsolvable problems. Okay? In a sense that they are not analytically solvable, usually. That's why we assume for time-independent Schrödinger equation, we create time-independent perturbation theory that tries to solve h psi equals e psi by presenting it as h0 plus v for the Hamiltonian, and then e0 plus e1 and up to higher degrees of freedom orders, right? And so we construct both psi and e in orders of v. Okay, so that's what perturbation theory does. It doesn't give you the total right answer, but it kind of gives you a way to approach the right answer by constructing the orders. Yeah.
That's 1 over infinity?
It's from 1 to infinity. Oh, okay. All of them. Yeah. Okay. Right. And so then there is a time-dependent version that solves time-dependent Schrödinger equation. And that's where we stop. So there is a time-dependent perturbation theory. And here is what we do is we present h as some h0 that presumably we know how to solve the time-independent Schrödinger equation for. And then there is some perturbation that is time-dependent. You can think of this perturbation as being, say, the typical example would be this is a molecular Hamiltonian, and this is electromagnetic field. Okay, so shine the laser, molecule, and you see what happens with the wave function. Okay, and so time independent we've done both non-degenerate and degenerate case. Yeah. Can try to remove it. A little push down. There's some buttons that I can reach. Yeah, you're right. Okay. All right. So then we stopped at time-dependent perturbation theory, and what we derived was that, okay, so psi xt generally psi 0 order xt plus first order xt and so on. Okay, and then 0 order was just something okay, I'll skip h bars for now. Alright, so 0 order, the way we constructed was that we had some initial wave function psi x0 which is expandable, is wave functions of h0 problem, h0 fn equals en fn, right? So we assume that we know how to solve this guy. Then our initial conditions, yeah.
Sorry, for the linear combination for your wave function, what's the superscript?
Here?
For the psi.
For the psi, 0. That's a 0 order. Okay. Okay, so for zero order, it's very simple. We are solving really h0 psi I deep psi dt, right? And the easiest way to solve this problem is represent psi, initial one, as linear combination of eigen states of h0. And then once we've done that, dynamics actually only requires the extra exponential prefactor, right? So that's the simplest way to build the solution for time-dependent equation if you know solutions for time-independent counterpart. Okay? So this part is easy. And then the first order correction was built also in a similar fashion. We assumed, okay, now let's put, instead of some coefficients, put unknown coefficients, dn's, and the spatial part is also represented with the same basis which served us well for the zeroth order, right? So this basis is complete, so whatever x part is, whatever spatial kind of dependence we have in our first order, it will be properly represented because this is a complete set, okay? And all we need is now to find the equations for dn's. And that's what we did by writing the first order equations, which is h0 psi 1 plus v psi 0 gives us I d psi 1 dt, right? So this equation allowed us to obtain equations for dn's.
How come we're not using the exponentials for the time dependence, and how come we're putting time dependence inside those coefficients that we can't just use the exponential right now?
Well, because this is only true for this problem, right?
Yeah.
So if we now dealing with the problem like this, that's exactly the problem that defines the psi 1. First order, right? So this is first order here, first order here, first order here, right? So we grouped all the first order terms.
Okay.
We can follow your advice. We can just say, okay, dn's are equal to e to the minus I ent, which is a bit strange, right? Or like, okay, so we say, all right, so there is a time-dependent part and there is time-independent part. Time-dependent part will be like this, and time-independent will be some coefficients, right? Why not to do this? Well, we can check that this is not going to be a solution for this problem. Okay? It's easy to check, right? Because you know how to differentiate. You know, we can just simply check, right? So h0 psi 1, what would give us? h0 will only act on these functions, right? So it will get us en's in front, then will be dn's, then will be exponents, fn's, and then v psi 0. Here, well, we don't know what v is, right? But it's some kind of operator, both space and time. V of xt acting on psi 0 is this with exponents cn's. Cn's, and then we have phi n's, and then exponent.
So it's the potential term that gives us the trouble?
Yeah. And then the derivative will get us something this-like, right? So I d psi 1 will give us en's dn tildes ent phi n's, right? And so then the right-hand side we'll cancel the first term in the left-hand side, and what we are gonna end up with is essentially Vxt Cn phi n ent equals 0. So, not very revealing, plus it's not really even true.
Yeah.
Right? So this ansatz is not enough, and the reason is that, well, dn's must depend on time. When they do depend on time, then you could have some derivatives of the dn part, right? dn over dt, right? And then you have this, and here instead of 0 you have those derivatives.
Yeah.
And then you can find from that condition what dn tildes are. So that's what we kind of did, because instead of this, we eventually introduced dn's equal to the exponents, and these functions, not constants, but time-dependent functions, right? And after doing this, we obtain equations for dn t, which we were able to solve. Was first-order differential equations, and the solution was like this. And this is general solution that may look scarier than it is really in practical applications. Okay, so, and then the only last bit of this expression I need to define, and m tau, it is the integral over space for phi n star x v operator. It's a function of space and time. We integrate space coordinate, and we're left with time coordinate. That's t here must be tau. So the same tau that isn't here, right? So we got matrix of functions because we have basis, and we integrate the space part. Okay? And that fully defines our first order. It consists of this part, this part, this part, and this part. 4 equations, yeah. Huh? This one? This is dnt, yes. It's a function that has an okay, so there is no phi x, yeah. Just dnt, the exponent, the extra exponent here, and then tildes. Tildes are defined like that. And kind of complexity comes from the fact that we considered very general initial conditions with a kind of linear combination of phi functions. Right?
So we want to actually think of those coefficients as having the exponential in them, in exponential times sometime.
Yeah.
That would be cool.
Right. So we first wrote the equation for this, and then the simple way to solve those equations was to do the substitution, where we put exponential function explicitly, and then we got simpler equation for d tildes, and then they were integrated. Okay. So similarly, you can actually do the second order. Yeah.
So you were talking about the complete basis there.
Yeah.
Just like related to this. So that's because they're independent, right?
This guy's a complete basis.
Yeah.
Yeah. It is complete basis because they are eigenfunctions of H0, some presumably physical Hamiltonian corresponding to physical observables, and they are forming complete basis set by postulates of quantum mechanics.
Generally, it's just kind of like cross nature.
No, but like you were just saying that it's a complete basis, but that's because, in relation to the question in the homework, it was not necessarily a complete basis, and so the difference then would be that this one has two that are independent of each other, two functions that are independent of each other.
Right. That is correct in general. That I guess that in an assignment, if you have Hamiltonian that this consists of x and b Hamiltonians, x and y Hamiltonians, right? And then you get the eigenfunctions fi of x and fj of y, right? So then and then you have coupling to make problem interesting. Then you have eigenfunctions of xy written as a sum over h psi equals e psi, right? And then psi is usually Cij phi I phi j, right? Tildes. So there is need for two subscript if both are them of those functions kind of coming from somewhere. You are defining them, and they form in complete set. You need to put all possible combinations. Now here the situation is different because we have complete set of this, and this determines what the dn's are. So dn's depend on the phi n's, right? In a sense, the solution for dn's depends on the choice of phi n's. That's why one subscript is enough here.
We have any time, so still.
Right, we can, and even here we can bring it to the form that has only one subscript, and that was the homework assignment, right? So you can only do the Cij phi j sum over j, right? Multiply by phi I. If you call this chi I, right? So then that it still depends on y, this still depends on x, but then the psi of xy is sum over only over y. I chi I y phi I x. Situation is very similar. We kind of said, okay, x basis is complete. Now these guys, their form depend on the phi i's. Indeed, phi I dependence comes from the coefficients, because coefficients will depend on what basis phi we chosen. And the same here, the fact that we set the phi ions here, then that defines the n's through, say, this matrix elements, for example, where phi's enter. So we change phi's here, and then the n's will be different, right? So in this one summation, these two functions, they are not independent. A set of functions depends on another, right, usually.
But just because they are not independent, that doesn't mean they form a complete basis set.
That's right. Well, some... Well, these functions, they're still given a freedom, right? So we are not... They have some freedom in them, but there is a part of the n's that comes just from the definition of phi n's.
Right,
Okay, so that's the situation. The same situation is in Born-Oppenheimer, where we have first electronic problem. So electronic problem kind of sets these functions, and then the nuclear part is dependent on the electronic functions. Okay, so because you can have different expansions, and the Born-Oppenheimer is only one of them. So the nuclear part of the Born-Oppenheimer problem is defined by the our choice for the electronic part.
So does that make it still a complete basis? Or not?
Yeah, it's the same as here. All right, so we start with a complete basis and of products, but then we can combine this set once we define the coefficients into these functions. And these products, they form complete basis set. Okay.
Since yi is parameterized by y, so you choose a given y, does that make your chi essentially a constant at that area?
Well, so for Born-Oppenheimer, what we do, we have electronic functions x that are parameterized by y, right? And then we have chi functions that are y functions.
And y is like the position of the nuclear part?
Mhm.
Okay.
Right. So these guys form a complete set for any fixed I, fixed y. These guys are complete set in x variable. Okay.
So it wouldn't be a complete set generally, though. You'd have to sum over all possible y.
Well, but you see, you are defining equations for this part. Okay. So indeed, if you already fix this products.
We're trying to figure out if we had a complete set in XY space.
Because that was your question.
So, sure, it's complete in X space.
Mhm.
We can move it around along X and Y.
Yeah.
It's like,
So this set is complete in the sense that you have products I and J
Yeah, we
functions,
said
right?
Yeah.
We have that, right? And then it can be written as a product set.
Yeah.
But in a sense, you do not use any coefficients. You already fix chi functions. Okay, so they are not forming in a sense the set. They are already defined because we define the coefficients, right? So whatever function you are representing with this complete set, you can represent that function with this construction as well. Okay.
But is that true of the bottom one with the parameterized?
With the parameterized, it's the same because, yes, you have some parametric dependence of these phi functions, but the main part is that x coordinate is complete. So you have function that set of function that's forming complete set in x. So you can, whatever function of x you have, you can represent by a linear combination of these guys.
Yeah.
Okay. More than that for a fixed y. So if you choose y, then you can use the set for that fixed y to represent any x function. Okay. So this is just your basis. You have not only one set of functions, like here, but you have multiple sets of functions. All of them are complete. They only have a freedom that you can change your y, and that will give you another set of complete functions in x coordinates. Okay, so you have kind of the even situation where you have more than one set, so you can use any of those sets to represent the f of x function, any arbitrary function, right?
But then if you fix y,
Yeah.
the chi's are then defined, so then you don't have the complete y.
Well, once you set this basis, right? Once you set this basis, you go and you formulate the equations for these functions, right? So you define in these functions only after you define the x part. That's why you don't put any restrictions in the y part, because the basis here is complete, and so you're getting all necessary information in y once you integrate the x coordinate. Okay, so that's why this construction is exact construction, and and it is in a sense exact, and it is easy to show that it's, well, similar to just grouping the terms. Okay, you can think of like imagining that there is y0, some fixed parameter, some fixed value here. So then chi I depends on y, and there is a counterpart which is forming complete set in x, and there is a fixed y. Now, in this case, you don't fix y when you were solving for chi, and but you potentially can do either this or that. This would correspond to the diabatic basis. One way to define the diabatic basis, where your derivative with respect to y for the phi I functions will be 0, so there will be no kinetic energy contributions coming from electronic functions. This is the simplest way to satisfy that, is to solve electronic problem only in one nuclear position, and then use that complete set to represent electronic states in other nuclear positions as well, right? Then the solutions for the chi I will be different than solutions for chi I here, because we're using different electronic counterpart for this basis, for defining this chi's, for defining this chi's. Okay. All right. Going back to this, we have solved the general case. Now to give you kind of some understanding what this all means for practical applications, let's just consider a very simple case where we start with one state and we promote a transfer to another state. And so if we take a situation where we have a particle in the box and we have phi 1 as particle in the box function, and our psi x0 will be just phi 1 x, right? There's phi 2 and so on and so forth. And so imagine the perturbation comes, okay, some kind of light, and it acts for a finite time. And the way perturbation will look in this problem time-wise for fixed x. So it's starting from 0, ending at time phi now. So let's make it sinusoidal. And then the spatial part will be, say, some constant, x minus L divided by 2, and then cosine omega t. So this is kind of our envelope, cosine function here, max at alpha minus alpha, goes with frequency omega. And presumably alpha is small to make perturbation theory applicable, and results in first order meaningful. Okay, so then just applying this formalism to this case, psi 0 xt will be just phi 1 exponent 1t, right? So it will go, t goes from, say, minus infinity to 0, and so on. So at 0 we turn on perturbation, and our psi 1 xt becomes dnt phi n's. So we cannot neglect the fact that our perturbation may excite, well, any state, second or beyond. And so now, just to calculate, let's just start with D2, right? So if we calculate D2, then the probability to find system at later time in the state phi 2 will be D2 squared, right? This is D2 is probability to find the system in phi 2x. Okay, and we can now write down the D2 T as D2 tilde exponent
So the phi sub n for our zeroth approximation for our first, like those are, it's the same basis functions for every approximation that we use, right?
Well, those basis functions are coming from our H0, right? And so the H0, the system we're considering here, is a particle in the box, right? Which we shine with the light, right? And the light, we shine it from 0 to TF, right? Pulsed it. And we now want to know, depending on the frequency of light, how probable will be to excite the system in the state phi 2.
And then, so we would get like a D1 from our zeroth approximation. And we would get
Well, D1, that's now my next point. D1 will be 0 because the way our perturbation depends on x, right? It's a linear function. And if you take the phi 1 and another function will be also phi 1 here, instead of phi 2 you put phi 1, phi 1, phi 1 connected with an odd function. So if you look at the picture, your phi 1 looks like this, and x minus L divided by 2 looks like that, right? So you multiply two even functions by one odd function and the integral will be 0. So that's why D1 will be 0 then. But D2 won't be 0 because we have D1, phi 1, which is like this. Coupling is linear, and then phi 2 will be odd function. So then phi 2 times phi 2 is odd. All right, so we multiply it by odd coupling and then even function, phi 1. So these two will be even again, and these two even, which means integral is not 0, right? So V21 tau is not 0. It's actually some function of tau. And not some, but, well, the tau dependence will be just cosine omega tau, right? Because this whole thing is just a spatial constant, essentially. Well, when we integrate spatial part, it will be just V21 constant. Okay? So V21 tau, it's going to be, just write it down, will be alpha V21 cosine omega tau. Okay? All right, so then we can put V21 tau here and actually combine all these expressions in the, let's just write D2 at the final time, absolute value. That's the probability we're looking for, right? And this factor is not important for probability because it will get cancelled since we're taking absolute value. And so this then will be just tau f squared with tilde, right? And then this will be alpha squared V12 squared, and all right, so then there will be 4 from kind of disassembling cosine into 2 exponents. Right, so 1/2 will appear, and once we square it, it's going to be 1/4. Disassembling this cosine is convenient to do the tau integration. Okay, so we have absolute value integral of d tau 0, and then okay, so then we will have the following 2 exponents: I delta E plus omega tau minus omega, okay, squared. Okay. All right, now we take a square. Oh no, wait. First we integrate. And then we take absolute square. Integration of exponents is very simple, right? So whenever we integrate first exponent and the second exponent, we just extra denominators. Okay. This is straightforward, right? Okay, so then, since we used atomic units, so what this delta E actually should be, it should be delta E divided by h bar, which we'll call delta omegas. Oh, sorry, let's, in my notation, I use omega 2, 1. Okay, so if we would keep track of h bar, then it would be not delta E, but delta E divided by h bar. So just unit-wise, delta E must be first divided by h bar so that we can subtract frequency. But in atomic units, h bar is 1, so you can write things like that. All right, now we have two terms, and the important consideration here in this absolute square, we have two terms. And consideration is the following, that one term will be much smaller than another. So the term where delta E minus omega, the denominator of this, if omega close to omega 2, 1, which is in atomic units delta E, then this term will be large. This term will be small because delta E and omega, they are comparable, so you have 1 divided by 2 omegas essentially, while here we'll have 1 divided by something small. Okay, and so it's called rotating wave approximation. To neglect this term where our frequency is far from the gap between the states we are considering. And so if we do that, we will obtain a very simple expression. A4. The I will be gone then from here because we're taking absolute square, and so we will be left with 1 minus f squared divided by this term. Okay. Because of this condition, say if our frequency of light is close to the so-called resonance frequency, which is the frequency that we obtain from the gap between the states, right? Then, as you can see, the denominator will contain the difference of 2, 1 and the frequency of light, so this will be very small number, right? So this term will be very large, while this term presumably will be much smaller because we have a sum of 2. So we're neglecting that other term. We are only left with this. Now there's some simple algebra we can do. Alpha squared v21 squared divided by 4. And then we'll have 1, these are all real numbers, 2, 1 minus omega squared multiplied by, if we take the absolute value of the 1 minus exponent, it will be 2 plus, minus exponent of I. And here I will introduce delta. Delta omega is omega 2, 1 minus omega. Okay. Short notation delta omega. And so from here we can see that what this is essentially 2 cosine of delta omega f. And the whole expression, if we represent cosine of this argument as a 1 minus sine of half of the argument, right, then we'll get alpha square v to 1 squared divided by 4 delta omega squared. And there should be 4 sine squared okay, and then to make this whole thing with delta omega divided by 2, we can multiply and divide by 4. So divided by 4. Here will be function sine squared. This is our probability to find. Our system in the second state, or first excited state, after pulsing it with light of frequency omega. Okay? Let's do a quick break and I'll tell you about this function that we obtained. What does it mean? So, if we plot this function, delta omega. After all, I guess it doesn't really matter whether we have delta omega divided by 2 as an argument or delta omega. There will be peak. So say we fix t and we study now f as a function of delta omega. So it will peak at 0, and then since it's a sine square, it's always positive. Right? And so there are some oscillations that are dying off pretty quickly, because sine is a function that stays between, well, sine square stays between 0 and 1, and this guy, when we increase delta omega, it decays quadratically, right? So this has a quadratic decay of amplitude. And so you can say that f is pretty much negligible after the first 0. And the first 0 of sines, these are at the n pi, right? So the delta omega t divided by 2 should be n pi, and n is, first 0 is pi. Okay, so that's what we got.
Sorry, what is f?
Well, just a function that we have here that carries the information about frequency and time, right? So we will study both. How does it behave with time, and how does it behave with the frequency difference? Okay, so right now you can make a conclusion that the closer the frequency of light that we use here in VXT to the gap between the states, phi 1 and phi 2, then more productive will be our pulse, right? So the population, the probability to find the system in the second state will be higher, because with delta omega approaching 0, we're approaching maximum of what we can get.
I thought it couldn't be found in state 1. Like, isn't that what we showed? That the coefficient d sub 1 is 0?
Well, d sub 1 is 0, but it's only first order correction, right?
Okay, yeah, that's right.
So we also have phi 1 still in the 0 order. Actually, if we think about this like in the framework of the spectroscopy, what happens is there are two types of spectroscopies. One is like just an old type absorption spectroscopy, where you shine light and you see how much of it is absorbed, right? We'll consider intensity of absorption with respect to the frequency, okay? And then intensity is, again, the closer we are, intensity correlates with probability, right, of getting function excited, system excited, right? And then the absorption will be as well better if we match the resonance frequency. That's why spectroscopy is valuable, as it allows us to see, probe essentially where the energy gaps are, okay? And that corresponds to just absorption. Now there is another more modern spectroscopies, which are coherent spectroscopies, and there I guess the basic idea is that you have system at phi 1, then you pulse it, you get also some phi 2, and imagine we tune our frequency of our light to phi 2, so others are phi 3 and phi 4 are irrelevant, right? But then still you have zero order function which is in phi 1 and the first order function in phi 2, so you have actually linear superposition of phi 1 and phi 2. And so your total wave function in the first, in the 0 and first order, right, say 0 and first, it will be phi 1 with some coefficient plus phi 2 with some coefficient. And this superposition, of course, will be evolving, oscillating between the two, phi 1 and phi 2. Those oscillations, they create emission of light because it's kind of a polarization, like the system essentially is polarized, and it now can emit, and you can detect that emission. And
so we're shining light on it, and while we're shining light, like while we're pulsing it's also spitting light out?
Right, that's right, yeah. Because it is in a superposition of two states, okay? Now, you need to be careful though, and that's why this spectroscopy is somewhat modern, because you have very many molecules in general in your sample, and well, they all may be slightly in a different environment, and so they may all kind of shine light out of phase somewhat. Plus, your light also must come in phase, so you need lasers to do that kind of experiment, because all this Avogadro number of molecules in a sample, they must be excited in phase kind of with your light, and then they should also emit light with the frequency which corresponds to the energy difference between the two states. And that emission, since even if they all emit at the same time, well, some of them, well, you need to be careful so that they will all be in kind of in phase. Otherwise, if some emit a little bit with a higher frequency or a little bit lower frequency, then they will dephase eventually, and you will lose signal pretty quickly. Okay, so there are some challenges. Cooling the sample would help you probably if your levels are close to each other. Okay, so it's more like an MR or EPR spectroscopy where you're probing the spin levels. Now, if you probe electronic levels, temperature doesn't matter much, because temperature doesn't provide enough energy to populate higher excited states. Okay, the typical energy scale is, say, like electron volts. 3 electron volts. That is in the wave numbers. 1 electron volt corresponds to 8,000, 8K to, and then 24K of wave numbers. And that's the typical electronic scale. Now, if we go to the vibrational scale, how nuclei, when they vibrate, what's the typical energy distance between the vibrational levels? That would be, I'll say, 100 wave numbers, very low frequency vibrations, to 4K, so half EV at least, right? So, but it's still much smaller than the electronic levels. Now, temperature, ambient temperature is 300 kelvins, right? And then that will translate into the 200 wave numbers. Okay, so it's very far from the electronic scale. And then, I don't know how much statistics you know, but essentially the populations of these levels is proportional to the Boltzmann factors, which are energy divided by kT. So if you have 8,000 in energy and 200 in kT part, so then you take the exponent of 8,000 divided by 200, 40, so it's exponent minus 40. That's the kind of a population you are talking about, which is very small number. So for excited states here. It can affect, though, low frequency vibrations. So the populations of, so usually you may assume, for like we did here, that only ground state is populated at the current condition. So then you pulse, and what you do is you excite. But if, say, you already have something on phi 2, right, then what happens is that the stuff in phi 2 will go to phi 1. So you kind of stimulate emission. Okay? And so to see some signal in NMR or EPR spectroscopy where the levels are very close to each other, you need to cool down samples so that there is some inversion between, so there is significantly larger population of phi 1 versus phi 2. Otherwise, all you get is kind of back and forth transitions that are not actually interfering with your pulse at all. So, so one absorbing and others are emitting. So, and then you are not getting, in this simple absorption spectroscopy, you're not getting any depletion of the intensity of your light or electromagnetic radiation. And when we talk about NMR, it's not light anymore; it's a microwave kind of range, because it's about like a few wave numbers essentially. Yeah. Right. So it's even lower than the lowest vibrational energy scales. All right. So now back to this f function. It gives us another interesting point here, is that with time it actually will grow quadratically. Okay, so how do we see that? Well, if we take, the simplest way to see this is if we take sine squared delta omega t divided by 2, right? Then delta omega t divided by 2. Let's remove t for now here. This is the function we have. Now we put t squared in the denominator and we'll put t squared in the numerator, nothing changed, right? But what this will give us is that if we take limit of this expression with delta omega going to 0, then we can cross the sine part divided by the denominator. It will be 1. And again, here it's the kind of physical level of accuracy or rigor, because what we essentially using is that limit of x going to 0 sine x divided by x is 1, right?
Another way, the first thing that I thought of was like the small angle approximation.
Yeah.
If omega is really small, it's
You see here, we're kind of first, why is it a kind of physical level of rigor? Because we have two variables, t and delta omega, right? And in math, if you are trying to take limits, of course it depends on which order you take limits. In physics, we're taking limits in the order that is more convenient for us, and I guess what we, to be rigorous here, we can say that we fix t to some finite value, t finite, and then we take the limit delta omega goes to 0, and we're getting rid of this, and we are having the t square dependence of the probability, right? So probability of being in the second state as time goes on depends on times quadratically, right? You may say at this point, wait a minute, but quadratic function will just keep growing, right? What does this mean? Well, it means that perturbation theory will break down at some point if you are in a resonance situation, okay? So it will keep just increasing the probability and will go over the 1 and will start producing kind of unphysical results, right? That you will have probability of finding system which is higher than 1. But of course, we won't use perturbation theory in that range. All it says is that probability growing quadratically with some, well, we didn't put coefficient here, so the coefficient, which presumably is small, will save us for some time, okay? And it's just to elucidate behavior of our function when we are close to the resonance. Because when we are far from the resonance, then the transition actually is suppressed by the delta omega, okay? So that's the peak that is growing quadratically. Okay, so another thing is that it's growing quadratically at another limit that we can use, that will be useful, is limit time goes to infinity for the function like this, sine squared alpha t pi t alpha squared. Okay, this is a definition, one of the definitions of Dirac delta function. Yeah. This is just definition of Dirac, one of the definitions of Dirac delta function. Okay? And it's conveniently, well, resonates with whatever we have in our perturbation consideration. For the following reason, because we can now say that our alpha in this definition is delta omega divided by 2, right? Then we can say that our f delta omega t, if we take a limit if t goes to infinity, this is equal to, let's see, it will be pi t delta function of delta omega divided by 2. I think it's right, because we need to multiply by t in denominator, then that means in f we need to compensate with now first power of t in numerator. Right? That's why t is here. The rest can be substituted by delta, and then the same story about the pi. So it didn't belong to our f function definition. So once we divide it by pi, it should also appear in numerator. Okay. So this is one limit, and another limit, I guess, would be the limit of delta omega goes to 0 for f is t square. Right? Both limits are useful. This is related to so-called kind of Fermi's golden rule, and also it's actually telling us that the longer we will observe, the more population will be only in the resonance level. Okay, so if here we have some frequency difference, right, between what system has as a frequency between first and second, and our light, which is omega. So if we do not shine exactly at the resonance, so that means we do not match the energy difference, right, and we're getting delta function, which is for any finite delta omega will be 0, right? So that's the long time limit. We're not getting any population. Okay? Now, how to understand this? If we go back to this picture and assume that, well, this is the sinusoidal plot, and maximum of population will be transferred to levels that are within the delta omega that is before the first zeros of the sine square function or sine function. So essentially all the states, why many states are coming here is that, now consider this, the following situation. You have phi 1, and then you have phi 2, and then you have many other levels close to phi 2. Okay? And then you do the excitation with this because of light, right, of frequency omega, and this is your delta omega from phi 1 to phi 2, but there are other levels that may be populated, okay, potentially. And if they are in the range of delta omega that is within the kind of this range, right? So here it's delta omega. Well, this is essentially pi. This is minus pi. Okay. So then all these levels will be populated somehow, because essentially the frequency of pulse will allow us to do that according to our expression of for the f function. And then if we analyze this expression further, it has time. So in a sense, the shorter is our pulse, the shorter t, then the larger delta omega can be, because they are related with constant. So 2 pi divided by delta omega is t, right? Or you can say that delta omega, that's what interests us, how many states will be significantly populated. this is delta omega, which is equal to 2 pi divided by time. So the shorter the pulse, the wider will be that initial envelope. So then with the longer time of the pulse, this envelope will start growing quadratically and will be shrinking. Okay? So that's where the delta function will appear. Right? In the long time limit, that envelope essentially will be shrinking, and I can plot somewhere here. Right? So a few situations. So say time is short or t is small. That would correspond very short pulse, right? And then nothing. For that short pulse, you will have function f like this, with a peak at 0. But the longer the time goes is long, or right. So say you do the sinusoidal pulse, which goes for quite a long period of time, then the f function will be more like a delta pulse in frequency, of course, not in time. So with shorter pulses, you will populate wider range of states. Okay? With the longer pulses, you will probe only the ones that are truly in resonance. Okay? And that brings us to so-called time energy uncertainty principle, which states that the delta energy, so to go from delta frequency to delta energy, we would need to divide by h bar, right? And so t would be in conventional notation delta t, so that's the duration of the pulse or duration of the perturbation of the system. So then we'll have delta E divided by h bar times delta t, and that's whole divided equals to 2 pi, right? And then h bar goes here, 2 pi times h bar, you will get just h. So delta E times delta t is equal to h.
Sorry, I thought that delta omega was delta E minus omega.
Delta omega was omega to 1 minus omega. That's right.
So that also equals. So isn't omega to 1 delta E though?
It's delta E of the system.
Yeah.
But here we're considering delta E, which is a mismatch of energy provided by light and the energy that is absorbed by system.
Okay, so
Okay? So it's essentially we are providing energy to the system that doesn't match the energy of the energy difference between levels. And we are looking at possible excitations, right? Say how many levels are excited and how far can we stretch this mismatch? Because say you have ground state, say you have a level, and you have only energy up to here, right? The question now, will you populate this level or not? And it turns out if you do short enough pulse, you can populate this level even though it's not in resonance. Okay, using this condition that at short time that you populate potentially many more levels than at the longer time. At longer time, you populate only levels which are in resonance, and the delta, well, this kind of time energy uncertainty principle allows you to say how many levels will be, well, involved in the excitation. Okay, if the V2 or Vn1 elements will be non-zero, of course, so that your light must connect whatever level you excite from to the levels which you are interested in, right? So if there is a whole manifold, then you only are constrained by the delta t, and that's why sometimes the short or femtosecond pulses, they're called broadband pulses, right? They can excite many vibrational states because vibrational states are close. If we now think about molecules again, then in molecules the situation is following. We have different electronic levels, right? And these are separated with electron volts, right? So they are far apart. That's why to make kind of a superposition of several electronic levels somewhat hard because they are separated far apart, and then you, in order to kind of, I'm talking about a superposition of, say, we start with the ground state, and we want to do the superposition of the first and the second excited state. Then with one pulse, you want to excite significantly, say, something here and something here, and they are separated with large energy difference. And how do you pulse it? With what frequency? If you pulse it with some frequency which is in between, yeah, sure, you have a chance to excite both, but your pulse needs to be very, very short. Okay? But realistically, femtosecond pulses, you can do back of the envelope calculation, because now we have delta E times delta T equals H, right? So then you can calculate delta E, which would be the range of states involved after a pulse, and then delta E will be in atomic units. It's we have 2 pi divided by delta T, right? Where atomic units means H bar is equal to 1. So now all you need is to put the kind of time scale of the pulse, right? Say time scale of the pulse 10 femtoseconds, which is kind of pretty fast. I think normal pulses are somewhat close to 40, 50. Yeah, so but say we push this to extreme of 10 femtoseconds, right? And then 2 pi divided by 10 femtoseconds. 10 femtoseconds, femtoseconds are not atomic units of time. The kind of 1 femtosecond is 41 atomic units of time. So to work consistently on atomic units, we need to multiply 10 femtoseconds by 41 in the denominator. So roughly then delta E, 2 pi, let's substitute it by 6. And then here will be 400. It's 41 times 10, roughly 400. And this will be roughly 1.5 times 10 to the minus 2 atomic units of energy. And that is 3,300 wave numbers. So that's the range which is in a vibrational range. So when you excite not only one vibrational state, but several of them. And that's why you can think of your new wave function on the excited electronic state being, well, similar to the original one, because it essentially will be comprised of different vibrational states that form complete basis. And you have enough broadband so that this wave packet will be transferred to excited state and will have the same shape as you started with.
We're also further limited that, I mean, when we're selecting sort of region like all our
Right, but Frank-Condon principle, but still Frank-Condon principle is just an overlap. Frank-Condon essentially tells us that the overlap, or the levels that will be involved here, they are involved as much as their Frank-Condon factors will allow them. And that's just the overlap of this function with the vibrational states on the electronic excited state, right? So, but potentially, yeah, you have all of them. And the Frank-Condon, there is a Condon approximation, and there is a Frank-Condon principle. And I think in this context, we assume usually that the coupling between light and molecule is given by the dipole. You can go over the algebra with starting with the classical representation of electromagnetic field, but what you end up with is your perturbation operator, which is a dipole moment, and the dipole moment is pretty much electronic variables plus nuclear variables and times electric field, which is a time component, envelope of your laser. Right, and then when you operate with a full wave function, which will be, say, nuclear function of ground state, electronic ground state, and then we'll transfer it with a dipole moment operator to excited electronic state, electronic, and then the excited nuclear wave packet that will appear on the excited state. Then we can see from this expression that out of these two operators, only the electronic part will survive, because of orthogonality of electronic functions. We will have two terms, chi ground, phi ground, electronic, chi excited, phi excited. And then here we're acting on electronic variables, then these functions are off the hook because they depend only on the nuclear variables. Our electronic functions, they depend on both electronic and nuclear variables. So what this term will give us is Frank-Condon factors, which are just the overlap between the nuclear components, right, times the ground electronic state, dipole excited electronic state. This is so-called transition dipole between the ground and electronic state, which characterize how bright the electronic state, or like higher excited state is, because some electronic states are bright, some are dark, based on the value of this dipole moment operator. Okay, and then this what will define which vibrational state this initial ground nuclear wave packet will go into, because potentially the chi of excited state, those are the levels, and the better the overlap between the ground wave packet and the levels which are eigenstates of, say, harmonic oscillator here. All right, so this overlap between this wave packet and this state, that's what will kind of modulate where this wave packet will go when you excite. And then the other component will be 0 because it will be chi g xn transition nuclear dipole. This is generally non-zero, but it's multiplied by electronic ground electronic excited state, and this guy is just 0 by orthogonality of ground and excited state. And then the Condon approximation is assumption that this thing doesn't depend, is not a function of nuclear coordinates, because potentially it is. since the electronic functions coming out of Born-Oppenheimer, they are dependent on nuclei. So this technically is a function of nuclear coordinates. So you cannot isolate the nuclear functions, and you cannot take just a inner product of them. You should have this function inside of that inner product, right? Technically. But what people usually do, they do the Taylor series expansion of this term and the constant part, which is the first part of this expansion. That's what they only live in, and that's Condon approximation. Okay, so then it's only back to the Frank-Condon factors that are defining where this wave packet will be excited. And this time energy uncertainty principle defines if you have a pulse, well, which states will be involved, because you have laser frequency and laser duration. Your laser has particular excitation energy, right? But because it's finite in time, it will take not only the state that it's kind of resonance in, but also states which are nearby. Okay, because of that, because essentially of this f function, it has a finite width at finite time. Only at the infinite time, it becomes kind of a delta function that zooms in into the particular resonance states. Okay. All right. Now, another thing that always to keep in mind is the symmetry aspect of the problem is that V to 1, or generally V and M tau, right? So which states are connected by the perturbation, that spatial part of the perturbation. So, and symmetry is very valuable tool here, because you can know in the symmetry of the functions and symmetry of the perturbation without even calculating the integral. You can say, okay, these states are connected, these states are not, and that helps. Also, the more intense field, that corresponds to larger constant in front of the perturbation, then of course the more the probability we will get after the excitation. This alpha we introduced, that was the intensity of the field. So it of course also will affect. All right. Questions? No? No questions? Okay. As for the last few minutes, let me derive clearly the so-called Fermi's golden rule. So the setup there will be that we have a single level from which we excite, or generally even it could be not a spectroscopic problem, but rather a problem that we have a level for a system, and through some external dynamics, essentially that level came into the contact with other levels. Okay, so there is kind of usually, if say you wanted to treat quantum mechanically a subsystem, and you don't want to treat quantum mechanically some other parts of your system, so you think of other parts like forces, external forces that bring some parts of your system into interaction, and so that's a valid approach. Then your quantum picture will be only on the parts that that you are considering quantum mechanically. Electrons and nuclei, probably one example where nuclei can be treated classically, and so they move and drive systems into the region where, say, electronic levels become close to each other, and some transitions may happen. Okay, but you may skip the fully quantum description of nuclei, rather consider them classically. Another case may be the electric field that you put your system in, right? So electric field, some kind of external field that you don't need to consider quantum mechanically, but it's rather driving force. So switching on and off that force can bring into, well, interaction some levels inside of your system which were not interacting. Okay? So the case here is that we have a level M, say, and then there is a continuum of other levels with some density corresponding to the energies, Ek. So there are levels which are very close to each other. We'll enumerate them with K. And there is a density, is like number of levels in some energy. It's kind of number of levels divided by energy difference in that range. And so now we also have coupling between K and M, and it's constant. So independent of K and M, it's essentially constant of K. So M is fixed, but K can change, but the coupling doesn't change, right? So our M level is connected with all other levels with a constant coupling. And so now the full transfer, probability of transfer, is a sum over K for the P. We're starting with M and we end up at K. Okay, so, and then we can try to use perturbation theory starting from this. It kind of goes to all the levels and may even come back. Okay, so this is equal to sum over K and all perturbation elements. And so there will be sine square delta K and tau divided by 2. Okay, so that's the expression for the discrete number of levels. Here again, atomic units, so you can substitute delta east for delta omegas, introducing the h bars, or you can keep the delta e's. For our consideration, it's easier to keep delta e's. And then, since the levels are close to each other, we can substitute this sum by the integral over levels. So we have sine function okay, and then the key here is we then in integral we substitute indexation or variable dk by the energy variable, and to have to relate dk with the energy, we introduce the density of states. Now, essentially, before we were counting the levels 1, 2, 3, 4. Now we're counting energy units, right? And then the density was the number of levels within that energy unit. Okay. So now we go by energies between, say, 1 kilojoule and 2 kilojoules. There's 1,000 levels, right? So we just introduce that 1,000 in the integral by putting the density of states. Okay, so that now we can go by energy units instead of just units of levels. And then there will be VKM squared keep carrying this constant, and then there's sine squared delta E Kn tau. Okay. All right, so now we assume that this was constant, have a constant density of states, constant coupling. So what this allows us to do is just to have rho E V outside the integral. Then we integrate dE minus infinity plus infinity. That's sine m Oh, we assume that it's constant.
Oh, right.
Okay. All right, and then what we do, we for large tau, we kind of use the fact that our f function, which is under the integral, right? So it's a delta function. Okay, and then it's delta function is a function which is very simple to integrate. And so what we get is by introducing the delta function will be delta of essentially delta E Km divided by 2. That's the delta function we'll get with some extra t, and so the rho will turn into the rho of Em. Then there will be V squared, and it will be 2 pi t. So that's the population growth. That we get in this problem. So in this problem, the result is that population transfer will grow linearly in time, and it all depends on the coupling and also the density of states close to our level from which we started. Okay, so the more dense system is in that region, then the faster the transfer will go.
I'm just kind of confused about what Fermi probability is.
So this is probability is a function of time, right?
Yeah.
And so that is your probability for as a function of time for the transfer from a single level to the continuum of levels. Okay. And so then you can also do sometimes Fermi's golden rule is put in the rate expression. So if you have a dp of probability versus dt, and that's just a constant, and then the constant equals to a rho of E m v squared times 2 pi. And sometimes it's written in the integral form where you have a delta function and the rho inside of the integral. Right? But whenever we have delta function, it's kind of you need to look for integral, otherwise, well, it's meaningless without the integral. So here we just integrated all the energy of the continuum, and we'll get normal expression without any delta functions. The delta functions will still be there if we try to write down the probability of going from M to a particular K. Okay, so these guys, as a function of time, will be rho at EM, the delta function of delta E Km, and then there will be V squared 2 pi, and then there should be time. Right, so then for state to state kind of transition, there will be a delta function. But at long time limit, eventually you end up in the level which is in resonance. All others are just becoming insignificantly small compared to that one level which is in resonance. Okay. All right. Next lecture will be given by Jessica and Hala.